Thank you for having me here today. Hello, everyone. Today we're going to be talking about MySQL Community Edition at CERN. My name is Abel Cabezas. I am a database engineer. I started my early career as a software developer, and after a short transition as a DevOps engineer, I became a database engineer. I've been working at CERN since 2019. I work at CERN. CERN is the French acronym for the European Council for Nuclear Research. It was established in 1954. It counts with 23 member states, and it sits astride the Franco-Swiss border near the Swiss city of Geneva. CERN's mission is to unveil how the universe works and what is it made of. And for that, CERN provides a unique range of particle accelerator facilities that enable the research at the forefront of the human knowledge. CERN also acts as a common place for people from all over the world to push the frontiers of science and technology. The most stunning machine at CERN is the LHC, or Large Hadron Collider. It is a 27-kilometer ring of semiconducting magnets that sits in a tunnel 100 meters underground and that can accelerate particles to nearly the speed of light. The most extreme conditions are met inside this machine. On the one hand, for the magnets to achieve its superconducting state, they're chilled to minus 271.3 degrees, which is almost absolute zero, or a temperature colder than the outer space. During the lead-ion collisions, on the other hand, temperatures 100,000 times hotter than the heart of the sun are achieved. As you can imagine, such a big machine produces a big amount of data, around 1 petabyte of data per second. But since not all of this data is interesting, neither its complete archival is feasible, only 1% of this data is kept. Here, the initial data filtering happens at the experiment level, and on a second step, this data is sent to the CERN data center, where an initial data reconstruction takes place. One copy of this data is stored for long-term archival at CERN, and another copy of the data is sent across the world to 170 different collaborating institutions spread across 36 different countries. All of these computing resources together conform what it is known as the WLCG, or Worldwide LHC Computing Grid, and its purpose is to analyze all the data that is produced in the LHC. CERN comes with its own IT department, and it acts as a service provider for the CERN user community, and among other things, we do databases. There are two main database services providing databases at CERN. One is the Oracle Database Service. It was founded in 1982. It was the chosen solution for the already extinct LEP accelerator, and it counts with around 100 Oracle databases. The idea here is to provide Oracle database accounts as a service. It counts with almost 12,000 Oracle database accounts, and it makes use of several Oracle enterprise level features like Real Application Cluster for high availability, Active Data Guard, Integrated Oracle Enterprise Manager, or RMAN for backup and recovery. It is a complex environment that requires a lot of business-specific knowledge to operate, I believe partly because it has been around for more than 40 years, and it had to evolve along with the organization in order to meet its needs. It is used by several services at CERN, from administrative information systems, passing by engineering teams to accelerators and experiments. Full DBO support is offered to our users, and in addition, we have an Oracle support contract. The amount of data that we manage is around 5 petabytes of data, and this is the project where I spent 50% of my time. The other 50% I spent it in the DBOD. DBOD is an acronym for Databases on Demand. It was founded in 2011. At that moment, there were a number of key applications at CERN that were running scattered around the laboratory, having their database server as MySQL, either because it was the only supported solution or because it was the chosen one because of its simplicity. I've heard some horror stories of people running production databases in their laptops or in their personal desktops. So with the idea of standardizing all of these deployments, a DBaaS service was born. The idea behind this service is to provide the users, to empower users to be their own DBAs. We just take care of making sure that the database environment is sanitized, is updated, and patched, so that the databases can run as smoothly as possible. It was designed because of MySQL, as I said, but it was designed in a flexible way, so it could accommodate other DBMS, as it was later the case with the addition of PostgreSQL and InfluxDB. It counts with more than 1,200 database servers, counting all together nowadays, among which MySQL still stands out as the most popular one. It is used by many key applications at CERN, like the in-house authorization and authentication service based on Keycloak, some experiment databases like Atlas or the LHCb, which are experiments of the Large Hadron Collider, or the WLCG file transfer service. This is the service that is in charge of transferring all the files that I mentioned in the WLCG slide to the rest of the world. All the data transfers are monitored through a MySQL replica. The amount of data that we manage here is significantly smaller, around 150 terabytes of data. And one remark that I wanted to make at this point is that despite providing similar things, the Oracle Database Service and the DBOD, they are not competitors at CERN. They coexist together. We are part of the same section. As a matter of fact, I work in two projects, and we are complementary services. When it comes to the deployment of MySQL, I would say it's a little bit particular. We run our databases either on VMs or bare metals, both on-premises data centers. We install several binaries per host, and we run several database instances per host also. In order to be more resilient to host failures or to speed up the process of migrating instances between hosts, we decided historically to run our databases with network-attached storage. This way, the full data directory sits in one NFS volume, and the binary logs are in the other one, also for disaster recovery purposes. There are at the moment 5 different types of deployments for MySQL. Single instances, which cover 90% of the cases. We have 2 main cases for replication. One would be replication for disaster recovery. In this setup, the replica sits in our secondary data center, and it is only used in case of the main data center blowing out or something major happening there. Then we also have replicas for scaling out reads. Unfortunately, since MySQL does not provide fully synchronous replication, the application has to tolerate eventual consistency, but as long as we keep the replication lag at bay, it should be okay. Then, since 2020, we have been introducing little by little HA solutions, first with the addition of a ProxySQL instance in front of a primary replica setup, and later on, our latest addition has been MySQL InnoDB cluster. So, what we would do before introducing ProxySQL is whenever there was a failure in a primary replica setup, we would just go out and perform a failover or manually or just recover the primary in time. But this is not a good approach, especially if you are called by an operator outside working hours or during weekends. So this is why we decided to go on and look on the MySQL ecosystem for a tool that could help us automate this manual procedure. We found ProxySQL. ProxySQL is a nice tool. It's an SQL proxy that comes with a built-in monitoring module that takes decisions on where to route the traffic based on the read-only or super read-only variables of the instances it connects to, but it does not come with a built-in failover or failback mechanisms. There is a good point. ProxySQL comes with a module called a scheduler. Scheduler is a cron-like implementation inside ProxySQL that allows you to extend its functionality. You can write scripts, either in Python or Bash, to extend the functionality. So profiting from this module, we wrote some failover scripts that will take care of promoting the replica whenever there is a failure in the primary while fencing out the failed primary so it does not come back again and causes problems. We also wrote some scripts for resolving split brain scenarios or for monitoring the replication lag so you don't lose data in case it is too far behind the primary. There is a problem with this solution. It is not a fully HA solution since it contains a single point of failure. It worked well for the purpose we wanted it for automating our failovers, but it does not represent an HA solution. It is not possible to run several proxies at the same layer. ProxySQL is not designed to take any decision on the topology it connects to. So we would have to add an extra layer to proxy SQL, and it would introduce a technical debt that we cannot afford. So this is why in 2022, we again went out to the MySQL ecosystem and started looking for a fully fledged HA solution. When we started our research, we had one thing clear in mind. The new solution should remove, of course, the single point of failure, while not adding too much complexity. It should be easy to deploy, easy to maintain, and easy to integrate. And after having tested different solutions, InnoDB cluster fit like a glove. It was the right tool for the right task. When it comes to the integration, it was almost seamlessly for us. In principle, you only need to integrate MySQL router and MySQL cell, since group replication is provided as a plugin of any MySQL server. But in our case, since our deployment is a little bit particular, I said we run our databases with network attached storage. When your database instance loses connectivity with the storage, you need a way to detect it, because group replication does not detect it. Your client connections will just hang there until a timeout is reached, but the group won't detect this as a failure. So we wrote a Python daemon that runs along any MySQL server that is part of a group replication, and that will take care of killing the instance if at some point during a consistent period of time the connectivity with the storage is lost or broken. Then the group replication will take care of performing the corrective actions. When it comes to the deployment, it was really easy for us. With MySQL cell, you have a lot of nice functions that can help you automate the deployment. You only need to connect all of these functions through rather simple scripts, and then in a couple of clicks, you have your router deployed, your InnoDB cluster deployed, sorry. When it comes to maintenance, it's again the same. MySQL cell is your best friend. It comes with a lot of nice features in order to automate the maintenance and life cycle of your cluster. Another nice things that we like about InnoDB cluster is the really well-documented procedures that it has. Either it is for a quorum loss or how to rejoin your instances to the cluster. It's a really good documentation. Another thing that we love is how easy it is to scale out reads. For the client, it's just as simple as specifying a different port in the MySQL router connection string. And if at some point your clients are struggling with the reads, you can just seamlessly add replicas behind the scenes. When you're managing a 1200 database server instance service, and you have a team of 4.5 people, you want to automate as many things as possible. Otherwise, especially if it is a manual and repetitive task. Otherwise, any task that lacks automation in your infrastructure is going to become a time-consuming task, devoid of enduring any value to your team, and that will scale linearly as your service grows. That is why we have been always in the process of automating as many things as possible. I have divided these automations into two different categories. On the one side, we would have user-facing automations, which are all of them exposed through a web interface, that simple, intuitive, yet complete web interface that we wrote for our users. From this web interface, the users can perform simple actions like starting and stopping their instances, modifying their MyCNF, reading log files, creating backups, to some other more complex operations like creating a clone of their instance, performing a point-in-time recovery, or now with the deprecation of UTF-8 MB3, perform an automatic character set conversion to UTF-8 MB4 from the web. When it comes to the operations automation, these are the automations that are behind the scenes that the users don't see, but that helps us deliver a better quality of service and to operate in a more reliable way. In this section, I wanted to highlight some of them. We have a service that runs in the background and that will continuously validate all the backups that we take in our service. So if at any point they're needed, we know that they are going to do what they are supposed to do. We also have automated workflows for migrating instances from one host to another, taking care of all of the pre-checks that need to be met, like is the port free in the host where I want to move my instance? Is the RPM installed there? And so on and so forth. We also have some other automations, like the detection of idle instances. When you have this many instances, when you have a big herd, you need a way to detect which ones are just for which ones you are allocating resources, but they are not actually using, so which ones you can recycle. One nice automation that I wanted to share with you, that we're proud of, is that the one that came with the upgrade to MySQL 8. Prior to MySQL 8, what we would do when a new MySQL release was coming out and we wanted it to integrate it in our service, we would just take this release, test our upgrade procedures in one of our reference instances, and if everything was working fine, we will just go out and enable it globally for all of our users. MySQL Cell comes with a really nice utility called the Upgrade Checker utility. The Upgrade Checker utility will go through your configuration file and check any system variable that is defined there and that will be removed in the target release, or it will also check for any system variable that is not defined in your configuration file, but that will change its default value in the next release. The upgrade checker report generates then generates then a report that we share with through cloud storage with our users, containing warnings and errors. If your upgrade report contains any error, this will most likely prevent your instance from starting after the upgrade, or the upgrade from succeeding at all. So now we have integrated this in our workflow. When a new release comes out, we just make available the upgrade path for our users, but we do not enable it by default. It is on their side to run the MySQL Cell on demand and go through the report until all of the errors are clear. Otherwise, they cannot upgrade. It is not safe to upgrade. And profiting from this workflow, we have also been able of enforcing the upgrade order of replication setups. It was not always well understood by our users, or only understood the hard way how to upgrade a replication setup. The only way to do it is to first upgrade your replicas and only then upgrade your primary. Failing to do so will cause any replica, which version is behind the primary version, to break. These replication channels will break. So yeah, just to wrap up the presentation, I would like to speak about the future of MySQL at CERN. MySQL is great. It's a key element of many services at CERN. And as such, we will make sure that it continues to fit in our service. And we will adapt to any new development that might come out, like we have been doing already with MySQL InnoDB cluster as a de facto solution, HA solution for our service. We have been doing it also with the promotion of UTF-8 MB4, and we will continue to do so with the investigation of InnoDB replica set as an alternative method for our current way of managing replicas, as well as with the clone plugin as an alternative method for the current method that we have. This is all I have. I hope you could learn something new, that you like it. Thank you very much.